Okay, in this video we're going to have a look at reversible reactions, and to do this we're going to use a little model that might help us get into this slightly easier initially and then expand this to help us understand the chemistry of it. Okay, so imagine we've got a box. Here's my box, and in the bottom of the box we put some liquid water. If I put this box into a room, then initially what will happen is we will start to get the liquid water will start to evaporate and it will turn into a gas. And as the gas starts to form, then the gas will condense and it will come back and reform the water. Initially we'll have a lot of evaporation going on with not much condensation, and as the gas starts to build up, and then we'll start to get condensation taking place, and these two processes, as this is left for longer, will just reach a point that they happen at the same speed. Okay, how do we link this to science? Well, this system here is being allowed to reach what we call an equilibrium. Equilibrium means that the reaction is going in the forward direction, in this case my evaporation, and it's also coming in a backward direction in terms of its condensing. So this reaction has got two different ways in which it can work, forwards and backwards. If we apply that to a chemical reaction, then I'm just using letters here to help me. This is how it would look. We can take chemical A and chemical B and react them together, and they will make, going in the forward direction, brand new chemicals, chemical C and chemical D. But because this reaction is reversible, chemical C and chemical D can also react and come back and make A and B. So this symbol in the middle we haven't seen before, but it means the reaction goes forwards and backwards, and therefore it's called a reversible reaction. Now with any reversible reaction, it's the same with this here as a model that we've just looked at. There will come a point when the speed of the forward reaction and then the speed of the backward reaction become the same as each other. And at that point we reach a very, very special point in this reaction. Let me explain a little bit more what that means. Okay, this point where this happens is called a dynamic equilibrium. Let me just cover this bit over for a second. I want you to imagine that you've gone to a shopping centre and you found an escalator, and the escalator is going down, and you are going to go the opposite way. Please don't go and do this, but you're going the opposite way and you're going to go up the escalator. And if you get your speed, so your speed going up is exactly the same as the speed coming down, to somebody standing side on looking at you, it looks like you're not moving, it's like you're stood still. When actually your forward speed is the same as the backward speed of the escalator. At that point in chemistry, we would say that you have reached what's called a dynamic equilibrium. So dynamic means moving, you're moving, the escalator is moving. Equilibrium means balance, because it looks like you're not moving and you're balanced. The speeds are the same. So we define this in chemistry as a point when the rate of the forward reaction is the same as the rate of the backward reaction. So in simple terms, the rate of you going forwards, the speed of you going forwards is the same speed as the escalator coming this way. You're not moving, but you are dynamic in that you're moving forwards, it's moving backwards. Equilibrium is a balance, it's at the same speed. When this happens in a reaction, so if I come back to my reaction here, the concentrations of these remain constant. So initially A and B react and form C and D, and then C and D start to increase, they'll start to react to come back this way, and then you get to a point where the speed is the same as we reach our dynamic equilibrium, and therefore the amounts of A and B and the amounts of C and D will just stay at constant levels. At that point we define it as a dynamic equilibrium. And it's worth we're going to go into this in further videos, but it's worth understanding that once we get a reaction that's at a dynamic equilibrium, we can change the conditions around it, and that will change the direction that the reaction will go in. So for example, if we look at changes to temperature or changes to pressure, we can change the direction either forward or backwards that this reaction will favour, and we're going to learn more about that in later videos. key points here is understanding that reactions are reversible, so they can go forwards and backwards, and understanding that a dynamic equilibrium is one where we are moving, but we're moving in the forward direction as the same speed moving backwards, and that in a chemical situation, that means all the concentrations will remain unchanged. They'll stay at a constant value for each one of those.